you get for free. All right.
So if I take something that's sitting in equilibrium, I pull it down, I let go, that's going to be the maximum that the spring will stretch. Amplitude. So that's just omega times the amplitude. What if there's a different way we can solve that same thing? Huh. Let's do it. So we need some running room here, so let's get rid of all that stuff. I'll leave this. There's a slinky. All right, so I have a slinky here. We'll pretend it's ideal for the moment. I add a mass. If I have the coordination, I will add a mass. Apparently not that way. All right, I add a mass. It now hangs down more. Let's shorten that some. I pull it down and I let go and it's oscillating up and down. Now this will eventually stop. It is damped harmonic motion, but if we think about the position of it, so I pull it down, I let go, and if I sort of walk that way with time, think about where the mass is with time. Well, basically the mass went up and then down and then up and then down and then up. What kind of function is that?
Negative cosine.
All right. Now I'm just going to change it around. I know we said up was positive, but I'm going to make down positive just to make it a cosine. Or if we plotted it, I'm forcing a cosine curve here. So my position is equal to some amplitude times the cosine of omega t. The generic equation, and this is the phase shift, which we're going to set equal to 0. Now, I feel like we've done this, and I might have done it in the other classes, and I just can't remember, but the slope of a cosine curve, have I done that in here? I know those who've had calculus should know it. I would expect them to know it. But
I don't think so.
No,
okay. So let's talk about the slope of a curve. I know that if this is a position time graph, I know velocity is the change in position over the change in time. So if I have a position time graph here, this is the rise over run. This is just the slope. This is the slope of position versus time. It's also the slope of displacement versus time. If I have a curve, the way you find the slope is you take a particular point and you're looking for the slope of the tangent line. So if I'm looking at a curve like this, I know that at the bottom, at the troughs, the slope is 0. At the top, the slope is 0. So I can so if that is position versus time, then my velocity versus time, well, I know it's 0 at the beginning, I know it's 0 here, I know it's 0 here, and 0 there, and 0 there. In this first region here, is that a positive or negative slope?
Negative slope.
Yeah, negative slopes go that way, so it's negative. And then in the next region,
Positive.
and so forth. And what is this graph?
Negative sign.
And if we did the
Oh,
slope.
yes, we did do
Oh.
this. But we didn't
You did
use
do
it,
the regress.
we didn't do it the graphing way, we just did it calculus way,
Okay,
or whatever. We didn't use the graphs to show.
alright, well, we'll do it the graph way now. If we did the slope of this, again, I look at the peaks and the troughs, and I know it's gonna be 0 there, 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 and there. And so the slope of this one, well, this first region, it's negative, and then positive, and then negative, then positive, then negative. And this would be a negative cosine curve. Just the flip of what we started with. If we kept going and kept it in slopes of slopes of slopes, the pattern is cosine goes to negative sine, goes to negative cosine, goes to sine, then back up to cosine again. The omega, if omega is bigger than 1, what's that gonna do to the graph?
Shorten it, whatever,
Which way?
horizontally.
Okay, so it's gonna squeeze it that way. So if I took this and I squeezed it, and let's go for a different color, for the usual reasons. Alright, so I wanted to. So the light blue line, is that steeper or less steep or the same steepness as the darker blue line?
Steeper.
Yeah. Because if I take any line, just think about it, if I have a normal line between my two hands and then I bring my hands closer together like that, it's gonna take a line from like this and make it steeper. So what that's gonna do is it's going to accentuate the slopes. And so if this is a cosine omega t plus 5, this would be a times omega sine negative a omega sine omega t plus 5. And then if we did it again, omega pops out again, and so I'd have negative a omega squared cosine omega t plus 5. So my amplitudes is that thing up front. So here, that's my amplitude there. My amplitude here is a omega. My amplitude here is a omega squared. Wait a second. My amplitude for my velocity is a omega. That's what we had over there. So my maximum velocity is going to be, assuming that it oscillates around 0, is a omega. My maximum acceleration should be a omega squared. The amplitude times omega squared. Let's see if we got that. So my amplitude was 0.3. So finding my maximum acceleration is a omega squared, and a was 0.3. Omega squared is just going to be
49.
49. .7 meters per second squared, and I'm pretty sure that's what we got before.
Where's the 7?
Pardon?
Where's the 7?
Where's the 7?
The 49 square, where did that 7 come from?
0.3 times 49. 3 times 9 is 27, so that's where the 7 comes from.
No, because you were saying 7 squared equals 49. Where did the original 7 come from, the omega squared? Am I just blind?
This-
19.6 divided by 0.4 is,
That's 7.
That's 7. Okay.
So when faced with a problem with something in harmonic oscillation, you have multiple approaches to it. If it's horizontal instead of vertical, Well, we've got the math's already in place. It's the same. This would be an identical problem if I took that spring, we figured out what the spring constant is, I now put it on a frictionless horizontal plane, pulled it out, 0.3 meters, let go. The math is all the same. All right, questions to hear? Oh. Now let's see how well predictions work. Yeah, it's gonna be a little bit awkward there, but we'll make it work. Stay on. All right, let's get this string out of the way. Now, the spring constant, if I'm dealing with a slinky, the spring constant depends upon how many coils I have. So if I had more coils, I'd have a lower spring constant because it takes less force in order to make it expand. So if it falls off, we're gonna have to start over. Someone was kind enough to leave a ruler behind. Meter stick would have been nicer. Anyone see a meter stick floating around here? Or a tape measure? Tape. That's the one I wanted. All right, here we go. All right, so the initial position of it is between the thumbs. This is precision measurement at its best. And about 19 centimeters from the bottom. So my initial position is 19 centimeters. .19 meters. I'm going to put a small mass on it. I'm going to trust the manufacturer, 20 grams. So I'll put a mass on it. 20 grams or 0.02 kilograms. If it touches the table, I'm going to have to go to plan B. Don't fall. Now, it is at an angle there, so what I'm going to do is I'm going to measure the high point and the low point, and then do the average. So the low point here is 29 centimeters. 29, so oh, wait, that can't be right. That's 49. It's 29, and the high point is about 30.31. So we have an average of 0.30. So putting on a 20 kilogram or 0.02 kilogram mass will stretch it 19 centimeters. The spring constant, therefore, is the weight 0.02 times 9.8 divided by how far it's stretched, which is 0.19 meters. And what is the spring constant?
0.032.
If I pulled it down and moved it up, now if I had a motion sensor here, I could actually get a plot of position versus time and do a curve fit, but we're not gonna do that right now. What I want to figure out is, ultimately, what's the period? Well, I know the period is 2 pi times the square root of m over k. We derived that last time. So that's 2 pi times the square root of 0.02 divided by 1.032. And what do we get for the period?
Uh, 0.8747.
Everybody else get the same thing?
Yeah.
Okay. All right. Units?
Meters?
Yep.
Radians, just
Oh,
Revolution.
Do it again?
Revolutions.
Not that would be angular frequency. What is period conceptually?
amount of times it takes to get around a circle.
Yeah, so what would the units be?
Seconds.
Yeah, seconds. We use a capital T for a reason. It's time. It is a time. All right. So I'm going to pull it down. Notice that the formula has nothing but with the amplitude in there, so the amplitude should not make a difference. So I'm going to pull it down. You've got a stopwatch. I'm hoping somebody's got a stopwatch. Just let me know when you are ready.
Gonna say stop as well.
We're going to do up and down 10 times, and then figure out what the average is. All right. Here we go. I'm going to do 3, 2, 1, go. When I say go, I'm going to let go. All right. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
1050 if I stop the little lead.
All right. So what are the numbers again? I heard 10 point something.
10.23.
1072.
10.22.
I had 10.50 if I stopped the little lead.
so
You stopped the lead.
what'd you get?
Like you said stop and it was like, it was around 0.3. And then I pressed stop and it was 0.5. Just don't listen to one.
Oh, so 10. Oh, it was 10 point something.
Yeah.
Okay. I thought you said 7.
Oh no.
So 10.4.
4.
Any others? So we add them up, divide by 3. We're going to get 10 point something. And then divide by 10 to figure out the time for one oscillation. We're not particularly close there. Why?
It's not ideal.
Right. So we have to somehow take the ideal into account. So let's do that. What is the average here?
10.28.
And so the time was 1.028 seconds per oscillation. It is not massless, it is damped. So to somehow take that into account, what we're going to do is we're going to adjust this mass. Because not only are we moving the mass of the 20 grams here, but we're also moving the mass of the whole slinky. So we're going to, so that mass right there really should be the mass of the 20 grams plus the effective mass of the slinky. So we're going to use our calculation here to figure out the effective mass of the slinky. Actually, what we're going to do is, yeah, we'll do it this way. So I have So 1.028 is equal to 2 pi times the square root of 0.02 plus whatever our effective mass is, divided by 1.032. And so, solve for effective mass. Nice if someone did it. So 1.028 divided by 2 pi squared, 1.032 minus 0.02. I suspect it's somewhere in point of something. And the answer is so it means someone else is gonna do it.
I think both of them.
I'm trying
So-
to.
You have a calculator right next to you and you're choosing,
ChatGPT's my god.
somebody get it?
I got 2.67.
You had 2.67? That just seems way too high.
I got 0.965.
0.965?
965.
Still seems more than I would expect. All right, this is roughly 1/6, so square